This is the fifth video in a series I created about restoring my Onkyo M-510 amplifier. Up till now, I tested the amplifier when I first got it. I compared its performance versus what it's supposed to be. I took the amplifier apart and reviewed how it's built mechanically, and I've actually begun replacing a lot of the components, mainly the capacitors. Now that I'm putting the amplifier back together again, in fact, most of it's already assembled now on my workbench, I'm starting to go over some of the electrical layout of this amplifier. This way I know what to look for while I'm assembling it, but also so I can start to consider some of the things I should look for when I go to turn it back on pretty soon. Now, I rely on the digital copies for service manuals and schematics. However, the ones that are currently available online are not the best quality. I was on eBay a few weeks ago and I typed in M510 amplifier, and I actually found an original service manual. I was rather surprised, seeing as not many of these amplifiers were built in the first place. So when I came across it, I had to buy it. It was not cheap, but I had to buy it. And I bought it so I could have it scanned and digitized. The quality, like I said, online is not very good, and the quality of these new scans is excellent. So if somebody is working on one of these, or if somebody would like to upload these copies to one of the online resources, please let me know. I'd be happy to give you a copy of it. I had the print shop also create new physical prints for the schematic. Now, the original schematic fit on 4 pages of 11 by maybe 8 by 17 actually. They were really small, and you actually needed a magnifying glass to see some of the letters, let alone actually trace out some of the circuitry. Scanning it, making it larger, and then putting it together in this type of a format, it's a game changer. Without this being able to actually follow through the circuits, I'm not sure how somebody would troubleshoot one of these. This schematic is pretty good compared to some of the other equipment from this era, from Pioneer, Sansui, for example. Pioneer, in my experience, probably has the best schematics. And this is somewhere in between that and Macintosh, okay? There are not a lot of reference voltages on these. It's not perfectly logical how it's laid out. It's not always left to right. And the way things are organized from a physical standpoint on this schematic don't always make a lot of sense in the real world when you're manhandling the parts. So in this video, it's going to be a longer one. I want to go over how the schematic is formatted. I'd like to go over where these physical parts are in relation to the actual parts on the components. And I also want to talk about some of the electrical components that make this amplifier special. I've already talked about its physical construction, how all these pieces are really made out of metal. I keep using these trim pieces as an example, but this is just one of 2 trim pieces on the faceplate, and it's made of brass. It's really incredible. This is a piece they could have easily made out of plastic, but they chose to use brass. And throughout the schematic, there's a lot of examples where a simple transistor would have worked just fine. But Onkyo used optocouplers. That's just one example of many I've found on the schematic, and I plan on going over those not down to each component level, but as a high level, just to show folks what makes this amplifier so special. So, thanks for sticking around to this point, and now I'm going to go through how the schematic is actually physically laid out, and then bring the parts over to it, so while I work through it electrically, I could point to where these parts are mechanically. Before I bring the camera in close to go over this schematic in greater detail with the components next to it, I just wanted to go over where the schematic is actually organized. Now, the power supply, of all things, one of the first parts of the amplifier, the power supply is actually located in the center part of the schematic. The relay output board is actually located directly in the center of the schematic. And then from left to right on the top is the actual signal path, if you will, from the power driver into the power amplifier, and then finally into the metering circuit for the front meters. And then finally in the bottom right corner, out by itself, is the protection and logic circuits. Only one channel is represented, and the opposite channel is copied on the bottom part of the schematic with its associated part numbers. Also, most of the reference voltages that you would need to troubleshoot this amplifier are located on the lower section. So while you go through the top section to understand how things work electrically, you would go to the lower section to then find out what are some of my reference voltages when I'm troubleshooting. I'm going to go over this starting with the power supply and then go left to right through the amplifier section and talk briefly about the metering section and then finally wrap up with the protection. Okay, I'm in the center of the schematic and the power supply is right here. Starting off with a plug rated for 120 volts. There's actually an addendum to this schematic for 240 volt operation. And at a real high level, the AC comes into the power supply and it passes through a bank of resistors that are either shorted or put in series with the power supply via a few power relays, 4 of them to be exact. There's an additional relay on each one of the mains before it goes anywhere, and that is what the protection circuit trips. Additionally, there's a bunch of extra parts on this power supply board that do interface with the protection circuit, and I'll get there once we get that far. Now, one of the most important parts about this amplifier are the in-phase transformers that confuse a lot of people, including myself. And they are located right here. So you have the AC power coming in to the main transformers, 2 of them, and then the in-phase transformers are located right here. And early on in one of my first videos, I talked about how these are configured. And this schematic actually does a good job of explaining that. The AC comes into the winding and comes out of the same winding. And they work in opposite directions to basically filter out some of the noise that might otherwise be present on the AC. That, in turn, cleans up, if you will, the power coming out of the main rectifiers. And then the main rectifiers feed into the filter capacitors. We're working right to left here, and then you'll see a bunch more rectifiers. That is one common thing in this amplifier, is every device has its own discrete power supply. I should have counted, but there has to be somewhere around 25 bridge rectifiers across this entire amplifier. This power supply circuit is located on the bottom of the amplifier. Again, it consists of the filter capacitors, the main power transformers, as well as those in-phase transformers. And on this one, I did replace the filter capacitors with new Panasonics. I made a video about that earlier on if you're interested in learning about that. So from left to right now, I'm going to follow where the signal actually comes into the amplifier. The first place that the power or that the signal comes into the amplifier is located up here. And this amplifier uses input relays that are controlled by the protection circuit to remove the input from the amplifier if there's a malfunction. That's an interesting thing I've never seen before. Also, there's two sets of inputs, one for variable and one for direct. The variable inputs use a potentiometer to lower the volume into the amplifier. It's like an attenuator. And the direct input essentially just bypasses it. You could be clever and actually use two different sources with this amplifier, just by one being connected to variable and one being connected to direct. Once the signals leave the first board, which is located on the back of the amplifier, it goes directly into the power driver circuits. Now, the power driver circuit, again, I'm not going to get too far into it, but the power driver is the first place where the signal is amplified. Typically, this is where like the first stage of some voltage amplification would occur. And this is also the stage where the negative feedback comes back to help stabilize and make the amplifier more linear. And that is the first main part that we see right here, is a little differential scheme. You'll see a lot of current sources all through this schematic, and you won't see a lot of electrolytic capacitors. Electrolytic capacitors are good because they're somewhat reliable, but they degrade the signal quality. And the only way to get rid of them is to make your circuit much more complex. And Onkyo chose to take that approach with this design. Now, once the signal leaves the power driver, it enters into the amplifier section. And this will be the most complex part of the video, because this is where the most interesting things, in my opinion, happen. Now, the power amplifier section is obviously on a large heatsink, and it's where all the power transistors are housed. This is also where all the emitter resistors, of course, and some of the protection are housed. Now, the first part of the power amplifier, so this from here this way, this is where the bias is set up in this amplifier. And what's interesting about this is a device called an optotransistor or optocoupler. And in these Onkyo schematics, it looks like this, which might be hard to see, but it's basically a transistor and a LED in one component. And these optocouplers are a way for control circuits, like this bias current string, to interact with a much more crude power circuit, or vice versa. In this case, this LED that's inside of a component is lit up based on some of the current in the output section, and it feeds back into a transistor that is located in parallel with the bias potentiometer. This is like a form of feedback, not like signal feedback, but some way to stabilize the bias current, probably from like a heat standpoint. Now, these optocouplers look like typical chips, but they have an interesting color. This is one right here, and this is one right here, and this is one back here behind the ribbon cable. The one behind the ribbon cable is the one used in this bias string. And since we're talking about the bias, this is where the bias potentiometer is. Now, I could go over this schematic as best as my abilities can, but again, like we saw in the power driver, you see a lot of current sources. You see like a diamond differential almost here in this stage. And not to gloss over everything, but all that part of the amplifier feeds into the main output section. And if you take everything away from this right side to the left, this part looks actually pretty straightforward. It's just a bunch of output transistors in parallel, a whole bunch of emitter resistors, 3 per each output device. That's done for a variety of reasons. Each resistor can be 1/3 of the rated wattage. And it also helps to stabilize the amplifier as well, because those 3 in parallel are more accurate than like a 1% resistor would be otherwise. Now, the output section starts here and ends here. But the rest of these devices are actually on this same amplifier board. And this is where some of the protection circuit actually starts. There's a lot to talk about here, but at a super high level, a set of additional resistors and diodes are set in parallel with a voltage reading between the rail and the emitter resistor, and it's averaged across all of the transistors to a point. And that point is actually floating, and it's compared to the rail voltage. When you set the bias potentiometer, the service manual actually has you check for 20 millivolts across these 2 terminals. And those 2 terminals are located on the positive and negative side of the amplifier, and they're located right here, P007, and right here, P006. That voltage is read as 20 millivolts, and when you do that, you are instructed to short terminals 4 and 3. Now, obviously, I haven't set the bias yet, and I haven't experimented. I'm not sure if that's totally necessary. The reason why you would short 4 and 3 is the output, or the left to right motion of this voltage, is what drives the protection circuit. So shorting 3 and 4 terminals actually takes the bias protection out of the picture. Now, again, we're still on the same board. That bias sensing string feeds into all these transistors. You have an interesting current mirror up here and here. This one uses the reference voltage off of a rail, whereas this one uses it from somewhere else in the schematic. And the way the service manual explains, it was done this way to eliminate false triggering of a high bias, but also it provides a quicker action if it does sense high bias. Now, all this feeds into another one of these optocoupler transistors. And this is the best way to see them. This is where they are drawn the biggest in the schematic. This upper one right here is that yellow chip, that optocoupler. And you could see how all these transistors drive the LED of the optocoupler. And when things are normal, there's no voltage across those terminals, so the light does not light up, which means this transistor is not turned on, which means there should be a higher resistance between 5 and 4, which creates a high signal when we get to the protection circuit. Now, opposite of the bias protection is the DC offset. That's a little bit more straightforward, and that's highlighted in this blue color. Basically, the positive and negative outputs, which are these 2 lines right here, are fed through a low-pass filter consisting of these resistors and then these capacitors, and is fed into a differential amplifier. So if things are balanced and everything is happy, we would have voltage across this LED. That's how this schematic is set up. So in normal operation, when there is no DC offset, this LED would be on, and because of that, these terminals 4 and 5 would have a low resistance, and a low signal would be sent to protection. Now, it's worth mentioning that these are inside of a chip, and that actually is an LED inside of the chip. There is no electrical connection between this side of the schematic and this side of the schematic. That helps to eliminate any type of interference or electrical noise from audio signals to like digital signals that we're using in the protection circuit. And then finally, The last piece of protection on this board is thermal. And it is a thermal resistor located right here. And physically on the amplifier board, it's mounted in between those optocouplers right here. And it's mounted right to the center mass of this heatsink. If it gets hot, that resistance changes. And once we get to the protection circuit, we'll talk about how that interacts. But basically that resistance changing picks up a digital signal over here in the protection scheme, and it trips a protection. That's a super high level, quick video of how this amplifier section works. Side note, I still need to take this apart, reapply all the paste, replace the few electrolytic capacitors that are on here, and also just check for scorching on the back side. I'm hoping there's no other issues with this because it's an absolute pain in the butt to get it out of the amplifier. And I don't want to put this together again just to find out. I have to take it apart. But yeah, this is the amplifier board mounted on a big solid heatsink. And that's how it's physically laid out in relation to the schematic. It's funny, the metering circuit is what draws everybody to this amplifier because the meters on the front are just so large and impactful, and the way the needles move is really clean and nice. But when it comes to going over how it works in the schematic, I'm just not going to spend a ton of time on it because it does exactly what you would think it does. It interpolates a voltage signal from the output and it turns it into a waving meter. That's basically what all this does, oversimplified. The one interesting part about this, though, is there's two discrete boards, one for each channel. They're located on front of the amplifier. And the part that I find interesting, again, is instead of just piggybacking a DC power supply and feeding this in parallel with some other, similar voltage in the amplifier, Onkyo went through the trouble, the cost, the expense, and the complexity to install its own power supply. So like I mentioned earlier, there's somewhere around 25 bridge rectifiers. Well, here's one. And there's one for each channel. It's all totally separate. It's very impressive that way. There's not much to go over here. Again, the electrical schematic is on top for one of the channels. And then the opposite channel is below it with the corresponding part numbers, or I guess device numbers, and a whole slew of reference voltages if you ever have to troubleshoot this board. And on this board is where all the different settings for like the 0 point, the damping, and basically like the range of motion for a given voltage. Also, this board has more of those optocouplers to keep any type of signal input away from the digital noise of some of these amplifiers. Because some of the protection circuitry is mounted on the amplifier board, the actual protector circuit board itself houses mostly logic controls. And this is the board here on top of the rear faceplate. Like most of the circuits in this amplifier, it has its own power supply. So you have AC coming to this board with the rectifier and a voltage regulator, and then a slew of chips. And all these chips perform functions that are outlined in this bottom right portion of the schematic. And these chips interpolate signals from the amplifier board for the DC offset, the bias control, and the temperature controls, which I outlined in the amplifier boards. In addition to those items, this protector board also controls functions with the stepped start. So what I mean by that is all the various relays that turn on when you first power on the amplifier. So this is like the soft start portion of the controls. And down here, this is called a warm-up simulator. And these are what drive the LEDs on the front of the faceplate to tell you at what stage is the amplifier currently operating in. So is it warmed up or not? The reason I put it in quotes is because it doesn't actually receive any type of voltage or temperature or current status from the amplifier to determine what step the warm-up simulator is actually in. What I mean by that is it's just a timer. And based on a given amount of time, from a time constant from these capacitors and resistors charging, different sets of those LEDs turn on. And it's done completely separate from everything that's actually happening in the amplifier. I would have assumed that these were tied back to like a temperature reading or a voltage reading somewhere, but that's just not the case. The reason why this is all so complex is because all the different various things that can trigger protection also blink the lights on the front of the amplifier. And this section here of the schematic basically outlines the control of that display. So these outputs here, these transistors basically used as switches, are what then coincide to the different various LEDs on the weighting monitor. And then everything else is basically what controls the input relays. So again, those input signals go through a relay. And also the main relay board, which is what turns the speaker relays off, and also stops you from turning the speaker relays back on if something in the amplifier is saying there's a fault. Again, this is a pretty complex design here. It's laid out fairly well in the service manual how it works. And, you know, fingers crossed, it worked when I first took it apart. So I haven't really dug into some of how all this logic works. But in theory, if you had an amplifier that was working correctly and you maybe ran into an issue where you lost a channel or protection was being triggered, there's enough ways here, albeit none of them are super straightforward, to find out which device is triggering protection, either bias, DC, or temperature. Those are your only three things that can trigger this board to lock out the speaker relays. Now, while I'm on the topic of this rear board, I have to talk about the bank of relays that are on this back faceplate. And these are, of course, the speaker relays, because here are the speaker terminals. These two relays here are controlled by the protection circuit, and they turn on when the amplifier is ready to produce sound. And there's delays built in, so this doesn't happen right off the bat. And then as you select system 1 or 2, these sets of relays pick up. And then also we have some inductors and resistors for just to stabilize the amplifier in case it receives some type of capacitive load. And the yellow wires are your negative feedback that go all the way back into the power driver board, all the way at the beginning of the circuit path. That's what these yellow ones are for. And then lastly, on this rear faceplate is the power cord, of course. And up here is where the input RCA jacks are mounted. I made this video in the series on YouTube because there's not a lot of information available online about these Onkyo M-510 amplifiers. I went over its physical construction and layout at a really high level, and we went over some of the more interesting electrical aspects of this amplifier. There is so much to be said about how this is designed electrically, but I wanted to keep this video as short as possible and cover the main topics. There are some amazing YouTubers out there. I'd hate to try to name them all, but some of my favorites are Mr. Carlson's Lab and X-Ray Tony B. There's so many more, but those are the first two that come to my mind. What I covered in this video doesn't even scratch the surface in some of the topics they honestly teach on YouTube for free. So if you're interested in this hobby, please check them out. Otherwise, if you're working on an Onkyo M-510, good luck. And since I have this apart, if you have any questions, please let me know and I'll be happy to help.